experiment this way, we'll do this kind of analysis. You can get around that problem. You can improve your chances of getting it right. There's a lot of that out there. But getting scientists to do it, or the journalists to publish those, or anybody to understand it is the problem. Microarray genetic analysis is something where there have been improvements because we now have genome-wide scan designs that do this a little better. But the early studies in this field were really susceptible to this problem. Because if you look at 20,000 genes at once, and you want to see if in a disease more of the genes are or how many genes are more or less active than they are in healthy people, if your test for whether they're more like that and less active is at the 0.05 level, you're going to get 1,000 of them that look like that, even if they're none. But so this is one example. An array tested 22,000 genes, found 13,000 with different activity. Actually, based on other research in this particular case, the scientists who did this study were able to come up with a pretty good estimate of how many genes were actually more active, and it was something like 1,000. You see, you're getting a hugely different. And it depends on what kind of disease and whether it's a disease where a few genes are way overactive or a disease where a lot of genes are just a little bit different. The statistics, I'm going to skip that, make it very difficult to draw sound conclusions. Clinical trials have huge problems. Everybody says randomized controlled clinical trials, the gold standard, and all this other stuff you do is meaningless unless you do it. Clinical trial, randomized and controlled, and that's the gold standard. To get something there, then you've got a definite right answer. You know what's what. That is below. That is so total below. The clinical trials have so many problems in it. Even if it all worked as it is ideally written down on paper with the randomization all just right and everything, it never works. It'd be wrong, but it never works that way because there's always mistakes. There's always people who are getting I know people who have been in clinical trials. They didn't know which group they were in. They went out and found the way to get the drug that was being tested. Okay, so they were either getting a dose of the drug when they shouldn't have been, or they were getting a double dose of the drug. And that's just, that's an anecdotal example, but it's just one of many things that can go wrong. But even when they go right, this idea that randomization makes it okay just to report an average at the end of the trial is baloney. There are individual differences that will determine what works and what doesn't, and those individual differences will not all be randomized. It's not even remotely thinkable that they would always be randomized. Maybe one trial would get really lucky and all the possible individual differences would be very well randomized, and I tell this to people who could, yes, well, they won't be, but the ones that are positive will be balanced out by the ones that are negative. Well, maybe. But, this was all done, this was all devised at a time when you didn't think there were that many differences. There are at least 1 million, technically I think, many more, but there's at least 1 million SNPs, single nucleotide polymorphisms in the human genome, where yours might vary from mine or anybody's at more than 1 million points. Now, if even 1% of those or 0.5% of those is relevant to what you're testing, that's thousands. And you can't expect a randomization of people to control and treatment group and clinical trial to randomize all those things. It wouldn't happen. And if it happened in one trial, it certainly wouldn't happen in all 20,000 clinical trials that are going on right now. So it's just really a problem in doing these trials. Averages, the bottom line is the average reporting of averages hides important effects. I'll skip through that. This is a point. Not all samples are representative. That's just, if you flip coins, it hurts times. I'm going to keep going. I'll go to meta-analysis. But anyway, the clinical trial problem, I think, is one of the most serious problems today. This is just life and death. It is literally life and death. There are drugs that would be beneficial for many people that are not approved because they didn't get a statistically significant positive reading in a clinical trial because the averages wiped them out.
So how do you know that they would be useful?
Well,
or beneficial, as you said.
Well, you know that they, because you have some instances where there are cases where you have found individual differences with people that you've identified who are the people who should get the drug and then it works for. And then you look at how the drug did not originally appear to be beneficial in a trial because the average results wiped it out. If there's only 10% of the people in the population who would benefit from the drug, it's not going to show up in the clinical trial. Okay. But if you have other evidence and you believe it is, and then you can do further testing and sort people out.
So you might want to test a subgroup of.
Yeah, you do subgroup analysis for starters. Is one way you sometimes find this out, and then but you don't always know what subgroups to look at. This is the problem. If you know what subgroups to look at, fine, you can do that, and then you can see, oh, it works for this group. But you don't know what, of all these different possible genetic variations, you only know they don't necessarily correspond to things like, sex and race and age, which you can easily see. They are things that you don't know. So the bottom line is the clinical trial system has not come to grips with this issue. And I think that, and it works both ways. Or some bad drugs might get approved because the detrimental thing didn't show up in the clinical trial. And that does happen. Then once it gets out in the population, you find out some bad things are happening to people that you didn't see in the clinical trial. But it's like, the system needs improvement. Anyway, so I'll say a couple words about meta-analysis, then I should leave a few minutes for questions, right? A lot of people think the solution to a lot of these problems is, well, you just don't rely on any one study, which is true. You should not rely on any one study. But you should aggregate studies so that you then get a bigger, huge sample size that will, if the effect is small, then you will be able to detect it. Because you can have a small effect that's a real effect, and it will go undetected by a statistical significance test if the sample size isn't very big. And it might be an important effect, even if it's small, if it's a drug that a million people take. But, so in principle, it's not a bad idea to do this. Collect those studies and add them up together. You can't just add them up. You got to do a lot of fancy manipulation of how you properly weight the data and put it all together and do your statistical tests. And then you can find out more things. Of course, meta-analysis depends on some assumptions. So it increases the power. It depends on a lot of assumptions. What makes you think you can actually justify doing these statistical tests on this data that you've just hodgepodge together? Well, you can justify it if what you've done meets certain criteria, such as, one, you've got all the studies that were done. If you don't have all the studies were done, you don't have a representative sample of all the studies that were done, and then you can't justify using the statistical methods that assume you have a representative sample.
You mean including the ones that were not published?
Exactly. If you don't, especially, because the ones that are not published are likely the ones that didn't find a big result or something, and so I'm going to try something else. And that, if all you got are the ones that were published, then you've really skewed the data to finding something that may or may not have actually been there, because the ones that didn't find it didn't bother to publish. So you cannot justify doing this meta-analysis, doing the statistics on meta-analysis, unless you get all the studies. If a bunch of them are off in file drawers somewhere, the legitimacy of doing the statistical test no longer applies. It also, to justify these statistical tests, you have to make sure that the studies have all done the same thing. They've looked at the same intervention on the same population, using the same definitions, same protocols. And if they haven't, it is true. You might not be able to find all these studies that are identical in every detail of every aspect of it, but if they're not, you have to then actually demonstrate that you have evidence to show that that wouldn't have made a difference. You can't just say, I don't think it made a difference. But if you're getting studies that are not comparable in the way they were done, that invalidates the whole underlying principle of being able to use the statistical tests to do the meta-analysis. And there are a few cases out there where good meta-analyses have been done and have been valuable by people who have been very careful and knew exactly what they were doing. But most meta-analyses get published are really pitiful. There's one that got a lot of publicity 2 or 3 years ago, I think. echinacea for treating colds. They did a meta-analysis and said, hey, it looks like echinacea is good curing the common cold. Well, this is a case where the newspaper account, which started out, oh, evidence that it cures common cold. And this newspaper, this is, I think this is the New York Times, actually, yes. The story would have been really good if they'd have put this quote like up at the beginning of the story. This like came at the very end. Of course, if they put it at the beginning of the story, then the writer would have probably realized they shouldn't even been writing the story to begin with. But the point still is, this guy hit it right on the money. If you're testing the same intervention on the same population using the same measures, then meta-analysis is a very good technique. But in this case, none of that was true. Why, a reputable journal would publish something like this that clearly did not meet the criteria for doing it properly is beyond me.
So can you tell me, can you tell us what they actually did in that?
In the echinacea study?
Yeah.
Well, they compiled a lot of studies that were not all strictly comparable. They used different protocols and things. Like, for example, the second example makes the same point. I'll do this, and it'll make the same point. This was a meta-analysis that was published in the New England Journal of Medicine, a reputable journal, usually, showing that the diabetes drug Avandia was responsible for causing excess heart attacks. And this guy, this Nissen guy here from Cleveland, who was the first author on this, is campaigned to get, and he succeeded in getting huge restrictions on it now. But this paper is crap. Here's what started out. This is where journalists really down on the job when they covered this paper. So in the Avandia group, there were 86 heart attacks. There's like 43 studies that were all compiled, and you add them all up. In the Avandia groups, there were 86 heart attacks. In the placebo groups, there were 72 heart attacks. A newspaper story said, look at this, Avandia groups, there were 85 compared with only 72 in the placebo group, showing Avandia increased the risk of heart attacks 46%. Well, any of the reporters who wrote that way, and that's all they said, they're morons. They didn't bother to look so far to see there were 3,000 more patients in the Avandia group. The fact that there were an absolute number of more cases of heart attack in the Avandia groups than the placebo group isn't the point. It did worse. The placebo group did worse on heart attacks than Avandia. Now, okay, so that's not necessarily means Avandia is off the hook, because you can't just add up the numbers and say this is better. You have to do the statistics. You have to weight these studies properly, and you have to put them together and do the analysis and do the math and all that. And when they did their meta-analysis in this paper, they found that even though in the absolute numbers it looked this way, it flipped over and it looked like Avandia was so many percent more heart attacks, responsible for heart attacks. Mm-hmm. But again, what justifies doing that? How can you justify analyzing data in such a way you take this lower risk of heart attack here and convert it into a higher risk?
Did they retract?
No, they kept going. They did statistical tests that came out showing that the Avandia group was actually worse when they weighted all the studies. And what justifies doing those statistical tests if you have studies that are all the same, studying on the same population, using the same intervention, same definition, same controls, blah, 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 blah. If you go and look at the paper, the place to start is looking at the control groups. In some of the studies, the control group was placebo. In some of the studies, the control group was a different diabetes drug. In some of the studies, the control group was Avandia plus another drug.
Oh, man.
There is no way you could justify doing that meta-analysis and drawing that conclusion, particularly when it contradicted the gross numbers. I mean, the gross numbers, granted, they are not meaningful in themselves because it's not legit to just add them all up. But if you're contradicting just adding them all up, you better have some justification for doing it. And they did. And I wrote something about the time that was baloney, and then shortly thereafter, a paper in the Annals of Internal Medicine came out that did the same kind of thing. They looked at this paper, looked at this data, and concluded, Just what I'm saying, that you did not